So I want you to imagine that you've just spent like 6 months architecting the perfect, infinitely scalable cloud environment. You have thought of absolutely everything.
Right, the dream scenario.
Exactly. You have your cross-region redundancy, your automated failovers, sub-millisecond response times.
Yeah.
You deploy the infrastructure as code, everything lights up green, and you log off for a well-deserved long holiday weekend feeling like, just an absolute engineering god.
Best feeling in the world.
But then Tuesday morning rolls around, right? You grab your coffee, open up your dashboard, and realize your brilliant, highly resilient architecture has single-handedly bankrupted your company while you were at the beach.
Oh, man. It is the visceral nightmare that literally every cloud architect carries around in the back of their mind.
Yeah, it really is.
Because we spend years learning how to build systems that survive massive traffic spikes or, regional outages. But technical perfection in the cloud has this massive blind spot.
Right.
Sometimes building a system that simply refuses to go down is the exact mechanism that destroys our operating budget.
Well, we are diving straight into that exact nightmare today. We're doing a deep dive on a really fascinating piece by software engineer and tech writer Aaron Rose. It's titled The Secret Life of Python the Sticker Shock, and it zeroes in on AWS cost anomaly detection.
Yeah, it's a great read.
It is. And our mission for this deep dive is to basically tear apart the hidden financial dangers built into modern serverless architecture and unpack the automated tools you need to stop a rogue deployment from torching your career.
Because we are really looking at what happens when code and finance just violently collide.
Exactly. And, okay, let's unpack this because Aaron Rose does something really effective here. He wraps these dense architectural concepts in a narrative.
Right. He doesn't just, hand us a dry white paper. He actually sets a scene.
Yeah.
We are placed in this grand Victorian library in London. It's described as this quiet, atmospheric place where the engineering culture is entirely focused on, craftsmanship and code quality.
Right, which feels so insulated from the chaotic, messy reality of actual business operations.
Completely.
Which honestly makes the impending disaster feel that much heavier. Like if you've ever worked in an environment where the code is treated like high art, you know the pressure.
Oh, absolutely.
So we're introduced to 2 engineers in this library. There's Timothy, who's a junior developer, and Margaret, the senior engineer.
Right.
And when the story opens, Timothy is not coding. He is staring at his monitor, completely pale, frozen with his hands clasped behind his head.
Which is never a good sign.
No. Margaret walks in, reads his body language, and assumes he just, dropped the production database or something.
Yeah, but his response is just one word. He just says, worse.
Oh, the dread.
Because he is looking at their AWS billing dashboard for the first time since they pushed a massive multi-region update a month prior.
Okay, so let's break down the mechanics of this crime scene. Because on paper, Timothy actually built a robust enterprise application.
He did, yeah.
To guarantee uptime, they deployed a multi-region failover architecture. They used DynamoDB global tables to replicate their data across different geographic regions, which is standard.
Super standard practice for high availability.
Right. But Timothy's discovering the hidden tax of that resilience. Because DynamoDB doesn't just replicate data for free. You are paying for replicated write capacity units, and you are paying for the cross-region data transfer out.
Yeah, that data transfer out is what always gets you.
Exactly. Every time a user writes data in London, AWS is charging them to ship that data all the way to Oregon.
And that baseline replication cost was already eating their margins, but the killing blow came from a single misconfigured Lambda function over in that Oregon region.
Oh man, this is the part that will make literally any developer listening wince. They had a serverless function that got stuck in an infinite retry loop.
Yeah. And, infinite loops in local development are just an annoyance, right? You hit Control-C, you kill the terminal, you fix your code.
Right, no big deal.
But in a serverless environment, an infinite loop is a financial catastrophe.
Because of how it bills you.
Exactly. AWS Lambda bills you based on the number of requests and the duration of the execution, which is measured in gigabyte seconds.
Wow.
So if an asynchronous event fails and the system isn't configured with proper idempotency checks or, a mechanism to just drop the event, the architecture just does exactly what it was told.
It just tries again.
It tries again and again. And for 4 entire days, this Lambda function spun endlessly before it finally hit a hard timeout. out.
The compounding math on that is just terrifying.
Yeah.
I mean, we're talking fractions of a cent multiplying thousands of times a second for 96 hours straight.
Yeah, and the result is a monthly bill that has completely quadrupled.
So Margaret walks over, looks at the screen, and she doesn't yell, which I found amazing.
True senior engineer energy.
Right. She just takes a sip of her coffee and diagnoses the problem with this term she calls the serverless cost paradox.
Yes, and the serverless cost paradox really gets to the heart of modern infrastructure. The entire selling point of serverless computing is elasticity.
Right. It's designed to scale infinitely and automatically.
Exactly. If your application gets hit by 1 million unexpected users, you don't have to scramble to provision new EC2 instances. The system automatically spins up the compute power to meet the demand.
Which, from a technical standpoint, is brilliant.
Yeah.
Your application stays up.
But the paradox is that the system has no idea what is a legitimate user and what is a bug.
Right.
It treats a recursive error loop with the exact same scalable enthusiasm as a massive spike in paying customers.
Because technical resilience without financial resilience is basically just a liability at that point.
Precisely. If the system scales automatically, the costs scale automatically.
You know, it's kind of like, think of it like a smart thermostat in your house.
Yeah.
Right? You give it an unlimited credit card and strict instructions to keep the house at exactly 72 degrees no matter what.
I like where this is going.
But then someone accidentally leaves the front door wide open in the middle of a blizzard. The thermostat is technically flawless. It senses the cold air, fires the furnace, and runs it constantly to fight the freezing temperatures.
Right, it's highly resilient.
Exactly. But because it lacks any broader context about the open door, it is going to absolutely destroy your bank account, doing exactly what you programmed it to do.
That is a perfect analogy. The system lacks context. It just executes the logic. And in this cloud environment, every single execution, every database read, every millisecond of compute carries a microscopic price tag that suddenly isn't so microscopic anymore.
Yeah, so Timothy is sitting there staring at this massive bill, rubbing his eyes, and he points out the obvious reality of a developer's life. He tells Margaret, like, I can't be expected to log into the AWS billing console and manually check the dashboard every single morning.
Right, because he has features to write.
Exactly. You can't have highly paid engineers spending their mornings doing manual accounting checks.
No, and Margaret's response is the pivot point of the whole narrative. She tells him he shouldn't have to check it manually.
Right.
Because in a mature engineering culture, you never rely on human memory or manual routines to catch systemic failures. You build automated guardrails.
So let's explore the first guardrail she introduces to stop the bleeding. Because she pulls up the AWS console, navigates into the Cost Explorer, and walks Timothy through AWS budgets.
Yeah.
And she refers to this as the hard line in the sand.
Right, because AWS budgets serves as the foundational layer of financial defense. It is the macro-level view of your project's health.
Okay.
You establish a monthly budget, say $10,000, based on what you expect the baseline architecture to consume.
But simply knowing you crossed the $10,000 mark after you've already spent it, that isn't really the goal here, right? By the time you get the invoice, the money is gone.
Exactly. The real value is in the forecasting algorithm.
Right. The forecasting is where AWS budget actually becomes actionable.
Yes. The system calculates your run rate. It analyzes how much you're spending per hour or per day, and it draws a linear projection out to the end of the month.
And if that projected line crosses your $10,000 threshold, the system takes action immediately.
The text details that it triggers an Amazon SNS alert, a simple notification service message.
So it pings your Slack channel or sends an email to the on-call engineer or whatever.
Yep. And the entire strategy there is compression of time. You want the alert about a massive cost overrun to hit your desk on day 3 of the billing cycle, not on day 30 when finance comes knocking on your door.
Right. It forces a shift from a reactive posture to a proactive one. When that SNS alert fires, the team can just pause deployments, dive into CloudWatch logs, and kill a rogue process before the damage scales.
Exactly.
But wait, I am looking at Timothy's specific timeline, though, and I actually have a major problem with using AWS budgets as the only defense here.
Oh, how so?
Well, his rogue Lambda function burned through a catastrophic amount of money in just 4 days.
Yeah.
Right? It wasn't a slow creep. It was a sudden, violent spike.
Ah, right.
So if AWS budgets relies on a monthly forecast, calculating an average run rate, isn't it mathematically just way too slow to catch a 4-day infinite loop in time? Like a monthly forecast alert might not trigger until day 3 or 4 of the spike, and by then the financial damage is already done.
That is a really sharp observation, and it's the exact limitation Timothy realizes as he looks at the console.
Okay, so he sees it too.
Yeah, because a monthly budget is essentially a blunt instrument. It is incredibly effective for catching slow, insidious leaks like maybe a developer provision an RDS instance that is a tier 2 large, and it's slowly eating into your margins over 3 weeks.
AWS budgets catches that easily.
Right, but for a massive hemorrhage, like an infinite retry loop,
Yeah.
the smoothing effect of a monthly forecast delays the alert. It is just not granular enough or fast enough.
So we need a micro-level guardrail. Like, if the monthly budget is the broad net, we need a scalpel to catch the sudden anomalies the absolute second they start spiking.
Exactly. And Margaret anticipates this. She moves past the web console and she opens up Timothy's IDE.
Ooh, moving to the code.
Right. They move from clicking through a user interface to writing infrastructure as code. She opens his AWS Cloud Development Kit, the CDK stack.
And this is where we get into AWS cost anomaly detection, specifically implementing the CF anomaly monitor directly into their deployment code.
And the shift in methodology here is profound because AWS budgets relies on a static, human-defined threshold. The human guesses the budget is $10,000.
Right.
But cost anomaly detection does not ask the human for a budget. It uses machine learning to observe the architecture in the wild and establish its own baseline of normal daily spending patterns.
For every individual AWS service running, which is wild.
Yeah, it's incredibly powerful.
And the text gives a really fantastic breakdown of how this machine learning model avoids alert fatigue. Because if you use static thresholds, you just get bombarded with false positives every time there is a mild traffic bump. Right?
Well, yeah, and then engineers just start ignoring the alerts.
Exactly.
Yeah.
But Margaret explains that the ML watches the system and learns that their DynamoDB global tables inherently run hot financially because of that heavy data replication we talked about.
Right.
So the model says, okay, I see this high spend, but it is consistent and expected. It establishes that high number as the new normal baseline just for DynamoDB.
It learns the unique financial footprint of the database versus the API gateway versus the Lambda functions.
And because the baseline is dynamic and service-specific, you aren't guessing at overall budgets anymore.
Right. Once the ML understands normal behavior, you supply it with one parameter, an absolute dollar threshold.
And in the code snippet Aaron Rose provides, Margaret sets the threshold to 50, just a hard dollar amount.
Which is such a critical detail. Setting an absolute dollar amount rather than a percentage deviation is crucial for cheap resources.
Wait, how do you mean?
Well, imagine you have a Lambda function that normally costs 10 cents a day. A 400% spike is still only 50 cents. You don't want to wake up an engineer for a 50-cent spike.
Oh, right. A percentage would trigger constantly on the small stuff.
Exactly. But if the machine learning model detects a sudden spike of exactly $50 above the established baseline for any specific service, the alarm bells ring.
Even if the overall AWS account is thousands of dollars under the monthly budget.
Precisely.
That's amazing. If a single serverless function suddenly jumps $50 above its normal daily behavior, the system flags it instantly. It catches the infinite retry loop on day 1, hour 2, rather than waiting for it to skew the monthly forecast.
And for anyone managing enterprise environments with dozens of linked accounts for different development, staging, and production environments, the text notes you can actually deploy this anomaly monitor at the consolidated billing level.
Wow, so it sits above the entire organization.
Yeah, it sits at the top, watching the telemetry of every single account simultaneously. Automated, absolute visibility.
So Timothy's looking at this infrastructure code, and he has this massive realization. He points at the monitor and says, this tool treats a cost spike the exact same way our dead letter queue treats a failed event.
That is the aha moment. It is the moment the junior developer finally understands the architecture of finance.
Because if you think about a dead letter queue, right, it is a foundational error handling mechanism.
Right.
When a toxic message enters an async queue and fails to process after a few attempts, you do not let it block the entire system or retry infinitely. You shunt that toxic message over to a dead letter queue where an engineer can safely inspect the telemetry and debug it.
And Timothy realizes they're doing the exact same thing with the company's money.
Yes, they are trapping toxic financial events. They have taken a terrifying, abstract business problem like going over budget and translated it into a standard engineering metric.
Which is brilliant. Cost anomaly detection is basically just an error log for dollars.
I love that. An error log for dollars. It just removes the panic entirely.
It really demystifies the finance side of the cloud for developers because software engineers do not want to act as accountants.
Definitely not.
But they inherently understand event monitoring, they understand automated thresholds, and system logging. So by writing the financial guardrails into the CDK stack, cost monitoring just becomes another unit test.
So Margaret nods at his realization, and she introduces the overarching philosophy behind everything they just did.
Yeah.
She says, welcome to FinOps.
Yes. Financial operations. It is arguably the most critical paradigm shift in modern cloud architecture today.
The text defines FinOps as a cultural practice and a cloud operating model that brings financial accountability to the variable spend model of the cloud.
And the history of that variable spend model is what really makes FinOps so necessary.
Right, because things used to be so different.
Exactly. If you think back to the days of managing on-premise data centers, infrastructure was a capital expenditure, CapEx.
Right.
A company bought 50 physical servers, they racked them in a cold room somewhere, and the cost was just fixed. The accounting department cut a check once. When developers wrote code, they just utilized the hardware that was already sitting there.
So if the developer wrote a highly inefficient, resource-heavy block of code in an on-prem data center, the application might run sluggishly, or, it might crash the server.
Right, it would cause technical issues.
But it did not suddenly cost the company an extra $40,000 over a holiday weekend. The financial risk was completely decoupled from the daily engineering output.
But the cloud is an operational expenditure. OpEx. Everything is infinitely elastic and heavily metered. Every compute millisecond, every gigabyte of RAM used, every data packet sent across a region, it's a microtransaction.
Which means developers are effectively making purchasing decisions every single time they push a commit or configure a service.
They are the new procurement officers. And FinOps is the organizational recognition of that reality.
Right.
It dictates that cost is no longer an accounting function dealt with at the end of the quarter by people in suits looking at spreadsheets. Cost is a core engineering metric.
Yeah, Margaret says it perfectly. Cost is a first-class architectural requirement.
Absolutely.
I mean, think about your own deployment pipelines right now. You would never push a critical application to production without monitoring CPU latency, database read times, or memory usage. So why are we deploying infrastructure without actively monitoring the financial burn rate at the service level?
Because an enterprise architect's job is not simply to build systems that survive region-wide data center outages. That is only the technical resilience.
Right.
They must simultaneously build systems that protect the company's bottom line, the financial resilience. The two concepts are completely inseparable in the modern cloud.
So if you were listening to this and you are building in AWS, Azure, or GCP, whether you are a junior developer staring at your first deployment or a senior architect designing global failovers, the lesson here is identical. Your cloud environment is not a blank check.
No, it's not. The freedom to provision infinite resources instantly must be aggressively balanced with automated, intelligent oversight. You cannot have the elasticity without the guardrails.
So Timothy goes back to his desk in that quiet library. He updates his architecture diagram and finally realizes his massive continent-spanning ecosystem is actually financially bulletproof.
Yep.
He has AWS budgets acting as the macro-level hard limits, calculating his run rate and sending forecasted spend alerts. And then sitting right inside his code, he has AWS cost anomaly detection using machine learning to establish dynamic baselines and catch those micro-level $50 spikes the absolute second the Lambda function goes rogue.
He closed the open front door, but the smart thermostat is still keeping the house perfectly warm. He achieved both technical and financial resilience.
We covered a massive amount of architectural ground today. We opened with the serverless cost paradox, where infinite scaling basically creates infinite financial liability.
Right.
We mapped the exact mechanics of a cloud billing disaster, from DynamoDB replication taxes to runaway async Lambda loops.
Yeah, the nightmare scenario.
And we explored how AWS budgets provides the foundational forecast alerts and saw how deploying machine learning anomaly detection via the CDK acts as a razor-sharp watchdog for individual services.
All of it driving toward the cultural mandate of FinOps, where managing money is treated with the exact same rigor as managing code.
Because the tools to exert absolute control over variable cloud spend exist today.
They do. They simply require the engineering discipline to implement them before the disaster happens, not after.
Right. Well, as we wrap up this deep dive, I really want to leave you with a final thought to mull over on your own. We've established that in the modern cloud, cost is a first-class architectural requirement, managed by infrastructure code and machine learning baselines.
Yeah.
But if a single tiny misconfiguration in a serverless function like a missing idempotency check can theoretically bankrupt a massive project over a 4-day weekend,
Yeah.
at what point does writing those financial guardrails become more critical to an engineer's job than writing the actual application features themselves?
Oh, wow.
I mean, if an infinitely scalable cloud architecture bankrupts your company, was it really perfect to begin with?
That is the defining question for anyone building in the cloud today.
It really is. Well, thank you for joining us on this deep dive into the hidden financial mechanics of the cloud. Until next time, keep your logs clean and your financial guardrails locked down.